So mid of November, we will notice the assignment 2. Okay. The deadline will be, the duration for this assignment 2 will be a month. So the deadline will be by mid of December. And there will be quiz 2 on the early December. Okay. So these two are remaining things. And also assignment 2 that will be related to implementing the segmentation and also the post estimation network. Okay. So the object detection pipeline is actually hard to implement by yourself. Okay. So you don't have to worry about detailed implementation, but you have to understand the concept because it will be contained in the quiz 2. Okay. So we are not, making this object detection pipeline as the implementation homework, but will be in the quiz 2 for for checking whether you are understanding the concepts. Okay. So we have learned this object detection pipeline in previous lecture. So one of the naive implementation of this object detector is using these sliding windows. Okay, and by cropping this region, you can apply the CNN architecture on it. But this may take a lot of time to achieve the object detection for an image. Okay, so this is inefficient and impractical. So the computer vision researchers are thinking about the practical way to use the CNNs in this domain. And before the deep learning, indeed some facial recognition approach or other object detector also uses this sliding window approach to achieve the object detection. Indeed, this is very famous facial detection algorithm called as Viola-Jones facial detector. They are using this sliding window and cropping the regions inside the window and using the boosting method and using the hand crafted features, which is called as hard-like feature. They extract that feature from the window inside the sliding window and then apply the boosting algorithm, which is the shallow learning algorithm, to classify that region as face or non-face. Okay, so this is one of the famous algorithm, but we cannot actually apply this scheme because CNN has a lot of parameters within it, so it may take a lot of time. It's impractical. So one of the way to achieve the object detection using the CNN architecture was using the object proposal. So we will extract some 1,000 to 2,000 regions that may have the object inside. Okay, that we will call that as object proposal, or we record that kind of algorithm as the selective search algorithm. And mostly those kind of approaches are using some heuristics, which assumes that inside the image, if some regions are having coherent color, textures, or other features, then that regions may contain object. Okay. So using this kind of assumptions, they are making some proposals, bounding box proposals from the images. Okay, so and they are assuming that within this 1,000 to 2,000 bounding boxes, if there is just one bounding box which contain the object inside, then that is actually successful case for them. They are believing that the CNNs can discriminate these 1,000 to 2,000 bounding boxes into object classes. I'm not sure why it is like this. No problem. 이거 이전 시간에도 이랬나요? 아, 그래요? 그럼 좀 참고 봐야 될 것 같은데. Sorry about this, but I think this is the problem in the screen. I don't know. Anyways, so the way to find this object proposal is achieving some segmentation. Segmentation, I mean, this is unsupervised segmentation. So they obtain this kind of map by clustering the features in the pixel-wise features. So for example, if we cluster, apply the k-means algorithm we have learned on the pixel values, the color values, then we can get this type of clustering map. That is, we can call as the segmentation map. So they are clustering the similar color pixels into one cluster. But I mean, we cannot control their, how to say, density, okay? So, I mean, some pixels are close to the other pixel with some criterion. I mean, if we set a coarse number of k values in k-means clustering algorithm, for example, if k is 50 and run the k-means clustering, that result might be like this. But if we set k is equal to 200 and run the k-means clustering, it may like this. Okay? So we cannot control their density. So the same object regions may have different number of clusters depending on this hyperparameter. Okay. So here, roughly, the color is similar, that they are clustered into the same cluster. But here, I mean, the subtle color difference may be result in the different clusters. Okay. Are you guys following this? Okay. So anyways, because we cannot control this type of things, in this selective search algorithm, they made different scales of the clustering map and use that to use as the clues to get the, I mean, object bounding boxes. Okay, so they also use color, texture, size, shape, other types of features to make this kind of clustering map and use that for estimating the bounding boxes. That's the object proposal, and it is also implemented in OpenCV. So you can use this one line of code to get the selective search bounding boxes. Anyways, the RCNN, which was the initial algorithm that achieved the object detection using the CNN, they are using these 1,000 to 2,000 bounding boxes extracted from selective search, and then apply it to the original image, and then apply CNNs for each region. So in this method, we have to apply CNN 1,000 to 2,000 times still, okay? So we have to apply CNNs for each boxes extracted from selective search and then make 1,000 to 2,000. So we have to apply CNNs that amount of time. And then after getting some feature, maybe this time the feature is one-dimensional vector, and we apply SVM classifier to classify that one-dimensional vectors, okay, to map them to the semantic classes, okay. But the limitation is still very slow. So we have to apply CNN 1,000 to 2,000 times. So it may take a minute, okay, a few minutes for us to achieve this object detection using this method. And also it is not end-to-end trainable, okay? So it is starting from these cropped regions to the object class. So we are losing some information while attaching these patches from the image. We are losing some valuable information. So that's not helpful for getting the best accuracy. So there is room to improvement. So fast RCNN, it is meaning this architecture is becoming faster than RCNN. And at the same time, their accuracy is also becoming robust. Okay? So this is published in one conference called as ICCB 15, the year of 15. But previous one, it was initially proposed in the year of 2013. Okay, so if you remember, the AlexNet, which is one of the successful CNN architecture that was published in 2012. So there's 1 year gap. Okay, so right after the computer vision researchers seeing the AlexNet works good for the ImageNet challenge, they are developing uh, the algorithm how that can make object detection successful using the CNN. And in this fast-start CNN, the idea is they are wanting to apply CNN operation just once. Okay. So, I mean, as I told you, CNNs are normally composed of two parts, the fully connected part and CNN layers. Okay. This is the input image. Then they are applying CNN first and fully connected layers later to get the one-dimensional vector, which means the probability vector. Okay. They are using only CNN, the first layers of CNN first, to apply it to the overall entire image. Okay. Then here they would have two-dimensional feature vector, two-dimensional feature array. Okay. This is a feature array. Okay, so this is denoting comp5 feature map of the AlexNet. So this is the fifth layer of the AlexNet, and which is actually this layer, just before the fully connected layer. So you will get two-dimensional array from the entire image. So, I mean, because the input image here is normally bigger than the images we are using for the image classification task, their 2D feature map is having larger dimension compared to that of the image classification task. And another thing is, in this feature map, 2D feature map, there's partial relations that was contained in the original image space is somehow retained. Okay, because that is characteristic of the convolution. So the convolution is locally summing the responses of the filter. So I mean, these CNN layers, they are retaining some features nearby these regions. And here, their features are retaining some regional information of this. Okay, so rather than applying the selective search bounding boxes in the image space, we can apply that kind of approach in the 2D feature map. Okay, this is very important idea actually. And thanks to this scheme, we can just apply this CNN operation just once. Okay, rather than applying it to the number of bounding boxes, we can apply this amount of operation just once. Okay, but the later part we have to apply. For the number of bounding boxes, but still they are greatly reducing the time complexity. But the problem was if we, attach the bounding boxes, the feature maps here, their dimensions are different each other. So depending on the bounding box size, their feature dimension is varied. Okay, but we have to fix the input size of the MLPs inside the fully connected layer, right? So we have to always define the MLP, their input dimension to output dimension. Okay. This is the main parameters of the MLP. Okay, we have to fix the input and output dimensions of the MLP layer. So to make their dimensions fixed, we have to apply some special layer, which is called as ROI pooling layer. So this is ROI means region of interest. Okay. So, for example, this is denoting the entire 2D feature map, and this is saying about denoting the I mean how to say the bounding boxes extracted from the selective search algorithm. We are dividing the windows into multiple regions, for example, 2 by 2, and selecting one or a few pixels from those windows. Okay, I mean, how large is this bounding box is not important, but the number of these subsections are now becoming important. Okay, and they are having the fixed dimensions. Are you guys understanding this? So, I mean, regardless of their width and height of the original selective search bounding box, we are dividing them into 2 by 2, and we can get always 4 pixels from this region, okay, regardless of their width and height, right? So using this ROI pooling, we can secure their feature dimension somehow fixed, okay, always having the fixed dimension, okay. And then we can now map them into the class probability and also the refined bounding box information. So this is the class information. If there are k object in our target classification object detection task, so they have the k-dimensional probability vector. And also this is the bounding box information. So one bounding box, there have to be explained by their center position and their width and height. So it requires 5-dimensional floating value to describing one bounding box. So anyways, they are estimating these two things, okay? And this is the loss for probability, which is same as closed entropy loss. And this is the more advanced loss function that is combining L1 and L2 distance metrics for the regression task, okay? They are similar to L2, but having slightly different scheme. Anyways, this is overall loss, combining this classification loss and the localization loss, okay? They are using these two types of loss to supervise these two final layers. And as a result, they want to update all the parameters inside the deep architecture, okay? And because now we are constituting all the layers in between the final output and first initial input. We are constituting them as the fully differentiable layers. So now we can say the entire architecture is end-to-end trainable. Okay, so starting from the initial input to the final output, all the components are trainable and differentiable. Okay. One merit of that is, as I told you, even humans are sometimes hard to say if this region is some object or not. Okay, seeing only this patch, sometimes humans cannot easily say what is the object for this patch. We sometimes also have to see the entire image to say which class this patch is having, right? But in previous RCNN, we are starting from this patch, and it was not easy for humans, even for humans, to say which objects are inside this patch. But because our features now is having accumulating some features from the nearby regions, okay? So it is similar to considering some context of the entire image when classifying these small regions, okay? So because of that, fast RCNN, the accuracy is also becoming higher. And at the same time, thanks to this idea that applies CNN operation one time, we can greatly reduce the time complexity as well. Okay, so this is one of the successful object detection algorithm, which is called as fast RCNN. But in 6 months later, another architectures are proposed by the same author, which is called as faster RCNN algorithm. So this algorithm, faster RCNN, you may, I mean, expect that this might be even faster than fast RCNN, and indeed it is faster than RCNN. So why it is faster than fast RCNN is they are inferring the object proposals. I mean, object proposals are coming from selective search algorithm before by applying some clustering algorithm and then classify 1,000 to 2,000 bounding boxes, which may contain objects inside. Okay. Previously, it was not differentiable because it is applying separate clustering algorithm on the entire input image and then filter out some bounding boxes afterwards. But the idea here is by extracting 2D feature array from the entire image, they want to do object classification as what fast RCNN does. Okay, this stream is same as before, but they are having another stream of algorithm that estimate object proposals from this entire, feature map. Okay, are you guys understanding this? So rather than applying clustering algorithm, which is separated from the training algorithm, they are also estimating the proposals from the feature map. Okay. So clustering algorithm, it is iterative algorithm, so it takes some time, but this is inference and giving this input, we apply convolutional neural network to estimate these proposals. In that sense, this is becoming faster. And also in that sense, it is becoming data-driven, which means optimal to the data. Okay. So they are solving some bottlenecks inside the region proposal side, okay, which is remained in the fast RCNN algorithm. Okay. So by doing that, it is becoming faster. At the same time, it is becoming more accurate. Okay. So this is the faster RCNN algorithm. So this is the comparison of these three architectures that could achieve object detection using the CNN pipeline in the early years. So this RCNN, fast RCNN, this is the faster RCNN. Okay, so RCNN, it is extracting features for all the image regions, okay, 1 CNN per 1,000 to 2,000 regions. Okay, and then we train another SVM classifier to classify region-based features. Okay, and it takes almost 1 minute, okay, to achieve object detection from an image. Okay, so this is some testing data. So their accuracy is like this at that time. And fast RCNN, it applies 1 CNN for entire image and extract feature from feature map regions and then classify those feature region-wise features. So thanks to this scheme, we are greatly reducing the time. Okay, so fast RCNN, it takes only few seconds. Okay, so almost 25 times improved. Okay, and slightly their accuracy is becoming robust. Okay, so compared to the 63%, almost 1% improved. And here they are further removing the bottlenecks in the region proposal side. Okay, and then they can 10 times improve the speed. Okay, so now it takes within 1 second. Okay, and the accuracy is also becoming robust. Okay, Are you guys understanding this? Okay. So faster RCNN is the state-of-the-art algorithm for object detection. I mean, before what transformer-based approaches comes out. Okay. So we will next time we will learn about the transformer. Okay. So we will also see how transformers are replacing the CNN-based architectures from next lectures, maybe. Okay, so now all the components are based on convolutional operations, but it is gradually, maybe from early 2020s, it is replaced by transformer. Okay, so we will learn about that. So transformer, maybe you are familiar with GPT. So GPT is abbreviation for generative pre-trained transformer. So GPT is also based on the transformer architecture. Okay, so everything nowadays is becoming composed of the transformer. So knowing about the exact mechanisms inside this transformer might be helpful to understand AI nowadays. But before that, I will explain about one more famous object detection algorithm, which is called as YOLO. Okay. YOLO, you may heard about this word. So normally it is called abbreviation of this "you only live once." Okay, so this is the famous word. I mean, used among young generations nowadays. You only live once, so enjoy your life. Okay, that's YOLO. But in this algorithm YOLO, they are replacing this live to look. Okay, so it is enforcing that it only sees images one time. Okay, so it is one of the efficient algorithm. Okay, I mean the fast RCNN method, they are called as two-stage algorithm. So, I mean, they first extract some bounding boxes and then they classify those bounding boxes. In that sense, they are called as two-stage method. They have to see the entire image once to make bounding boxes. And then because there are many bounding boxes, they have to classify those bounding boxes into classes, and that is also we say that is also seeing images one time more. So we have to see the images almost two times. So in that sense, this RCNN is called as two-stage algorithm. But this YOLO is one-stage algorithm. They are indeed getting bounding box and class probability for each region simultaneously. Okay, so they see once for the entire image and then estimate these two jointly and then filter out unnecessary regions to get the final output. So in that sense, they are very efficient algorithm. In their name, they are saying they only look once for the image. Okay, so it is indicating that they are very efficient. So this is the YOLO architecture. So given the entire image, you can see their input image is larger compared to the image classification network. Normally, image classification, their image size are around this, okay, but almost doubled because object detection, we have multiple bounding boxes inside, and the images are composed of multiple objects. So we may need larger scale image to secure the object's resolution. Okay, but in the image classification, we are assuming that images are composed of only one object, so we can reduce the resolution of the image. Okay, so this is normal image size in object detection. And in the final layer, you can see their dimension is like this, 7 by 7 by 30. Okay, but inside, they are also having FC layer and other convolutional layer and Google LUNet architecture as the backbone. They first use the Google LUNet and then having multiple convolutions and apply FC layer to map it to 7 by 7 by 30 dimensional output. So all of these intermediate layers are differentiable, so you can train that using the using the gradient descent optimizer. But more important thing here you have to note here is 7 by 7 by 30 dimensional output. Okay. I will explain that. Why 30 dimension? So that 30 dimension is actually composed of this. So here, their default setting is they will estimate 2 bounding boxes, and each bounding box information is composed of 2 5-dimensional floating values. So I will explain why it is like that. So 5-dimensional, these floating values are reserved for 1 bounding box information. So we are estimating 2 bounding boxes. So 10-dimensional information is reserved for the bounding box, okay? And remaining 20 is for class probability. So because in their data set, in the default YOLO algorithm, they are dealing with the data having 20 classes, okay? So because of that, they are estimating 30-dimensional output, okay? And why 7 by 7 is here they are dividing the entire image into 7 by 7 grid, okay? So they are dividing the entire image into 7 by 7 grid. So there are, in their output, they are having 30-dimensional information for each grid, okay? So that's why their output looks like this. So here in the figure as well, they are denoting that. So these are 2 bounding box. They are wanting to estimate 2 bounding box for each regions, okay, each grid, okay. And then they want to estimate 20 class probability for each grid, okay. Are you guys understanding this? Because of that, this figure is denoting that this amount of output values. Okay, for 7 by 7 grids, they are estimating both 2 bounding boxes and 20-dimensional vector, denoting the probability vector for object classes. Okay. So actually, these two are denoting this pipeline. Okay. Using this pipeline, they are getting this one time from the this operation, okay? And this is denoting these 2 output. Okay, are you guys understanding this? Yeah. So indeed, the YOLO is seeing images one time to get bounding boxes and probability vector simultaneously. Okay. And I will explain why one bounding box has to have a 5-dimensional vector. Similarly to previous, I mean, when describing one bounding box, we need x and y, their center positions. So this is x and y, and also width and height we need. So for floating values for explaining about this location, and the C is the last one, which is different from that of the fast RCNN. This is indicating the confidence of this bounding box, which is indicating that a certain bounding box is having object inside or not. Okay, so For example, the bounding boxes extracted from these regions, they will have two bounding box estimation from this region because this is the grid which have object, the bicycle object inside. Their ground truth is this, the ground truth for these confidence values are becoming one, indicating that their grid is having object. But if grid is here, if the two bounding boxes are estimated from this grid, because this grid is not having object inside that grid, their confidence value have to be close to zero. Okay, so they are making ground truth for each grid when supervising this dimensional output. For each grid, they are making this same dimensional output as the ground truth and setting this confidence value as zero if that grid is not having object inside, but making this confidence as one if that grid is having an object inside. Okay. Are you guys understanding this? Okay. So as a result, from 7x7 regions, okay, they are estimating two bounding boxes. So there are resulted in 98 boxes. Okay, so here they are estimating 98 boxes with 20 with a probability vector that is denoting the probability for 20 classes. I will explain this first. So this is the initial result that is coming from, if you plot 7x7x30 dimensional output coming from YOLO, their output, if you visualize them, there will be many output that is closely estimated, okay? So in later stage, you have to apply non-maximal suppression algorithm to filter out non-maximal responses. So among these, what they do is among these multiple estimations, you choose one bounding box which has the maximal confidence value and removing all others. That is called as non-maximal suppression. So if some boxes response is non-maximal, we want to always remain one maximum responses. So we are removing non-maximal output. So that is called as non-maximal suppression. So this is very heuristic algorithm, but anyways, it is helpful for us to achieve the final classification. So here it is indicating the non-maximal suppression algorithm. So given this many output, we are applying non-maximal suppression, which is called as NMS, to achieve the final object detection. Okay. So, this is the YOLO algorithm, and you may think this is not perfect because this is too simple sometimes. So indeed, the performance of YOLO is limited. Their algorithm is very fast, very efficient, but this algorithm is actually weaker than their performance is actually weaker than that of fast RCNN or faster RCNN. But YOLO version 1, I'm explaining about YOLO version 1 now. This is YOLO version 1, which is introduced in the year of 2016. But now we have YOLO version 12. Okay, so it has been 10 years after we have YOLO version 1. So there have been a lot of algorithmic improvement. And we will see what YOLO version 2 and what YOLO version 3 in later lectures, how they implement YOLO version 1 to YOLO version 3. So there are some tricks to improve their performance, and there's some trade-off when they add some algorithm. their time complexity is becoming slightly, becoming slow, but their performance is becoming slightly improved. So YOLO version 2 and 3, they are already surpassing the performance of RCNN and fast RCNN and fast RCNN. So YOLO version 2 and 3, they are becoming better than fast RCNN. At the same time, they are becoming efficient compared to the fast RCNN. So nowadays in companies or other practical situations, this YOLO is more preferable, okay, because they are fast and at the same time they are robust, okay. And after that, the YOLO is maintained and they are now having version 12, okay. So if you are interested in YOLO, then you can also search for their technical report. So, but YOLO version 3, till YOLO version 3, the algorithm is maintained by original author of YOLO version 1, and also they are having publication. Their algorithm is well maintained as the technical report or paper, but after YOLO version 3, the author is not anymore maintaining this algorithm, and their algorithm inside is not publicized well. So it is hard to see what exactly their algorithm is having, but there are available. So if you are interested in, you can search it for the maybe document. Okay. Okay. But this is the initial YOLO algorithm. So I'm teaching that. Okay. And the loss function is not that difficult, but yet at initial, if you initially look at this loss, then it is seemingly complicated, but this is not that complicated. So this is the L2 loss, which is the MSC loss, which is applied to the bounding boxes. So when describing the bounding box, their center position XY and their width and height, we have to apply their ground truth to make their prediction close to the ground truth. Okay. And these, you have to notice that these kind of losses are applied to each grid. This S is denoting 7. So this means each grid. So even though I explained the original authors are using this 7 by 7, but the number of grid that can be changed, freely changed before training, okay? So freely change it by yours before training, okay? And also, I mentioned that they are using this 30-dimensional output because they are estimating 2 bounding boxes for each grid, and they are 20 classification problem, right? But of course, this could be also changed, and also these values are resultantly changed. Okay, so you can manage change these hyperparameters, and because of that, the 7 we in loss functions they are denoting that as S rather than just stating that as 7, and also this B is denoting 2. So for each grid, they are normally finding 2 bounding boxes, but we can say in general they are estimating B number of bounding boxes. So this is 2, but we denoted as B. So this is 7 squared. So for all the grid and for all the bounding boxes inside, if they are grid which have the object inside. So there's one more condition for applying this rules. So as I told you, they are applying this only for the grid which have object inside. Okay? That is indicated by this flag. This is becoming 1 for the grid that have the object inside, and this is becoming 0 for the grid which is not having object inside. Okay, are you guys following this? So this is applied only for the grid having object. So for the grid having object, there how to say, there these values, which is indicating x, y, their center positions, they are applied with their ground truth. But for the grid, which is not having object, this supervision is not applied because it will not be used during the inference. And also, this is also same thing. Okay, they are applying for all the grid, all the bounding boxes in the grid. If they are having object inside, they are applying this loss for the width and height of the bounding box. Okay, this is very simple. I mean, even though they look very complicated at first glance, they are very simple. Okay, and also this is also the thing what I mentioned before. So this is the first dimensional information. Second, I mean, in this fifth 5-dimensional vector that is denoting the object bounding box information. This is first dimensional, this input, this information. Second, this is y, center y, and this is width and this is third and fourth information. And this is the confidence value, which is the last information, which I denoted here, right? That is also applied with confidence ground truth. So as I told you, for all the grid, for all the bounding box estimation, if that if that grid is having object, we will apply that confidence close to 1. Okay, are you guys understanding this? And also, if that grid is not having object inside, then this flag is turned on. This flag is turned on for no object grid. So for the grid, which has object inside, this becomes 1 and becomes 0 for for bounding boxes which does not have object inside, this becomes 0. But this is doing the opposite things. For the bounding box, for the grid, which is not having object inside, this becomes 1. And for the grid, which has the object inside, this becomes 0. Okay, are you guys understanding this? Easy, right? Okay, so no object. Okay, and if that grid is not having object, this is becoming 0, and this is the ground truth is having 1 for object grid. So their prediction is close to 1, but for grid which is not having object, their confidence value is forced to go to 0. Okay, and also this is denoting the closing the probability for each grid. So they are not having this summation anymore because this is for only grid, iterate for each grid. For each grid, they are estimating, they are supervising the 20-dimensional vector, to make it close to their ground truth. So rather than using the cross entropy loss here, they are using MSE for the probability. I don't know why, but still works. Okay. So this is the loss function that want to supervise this dimensional vector properly estimated from each grid. Okay. Are you guys understanding this? So, I mean, this is very, it looks complicated, but it indeed doing the same thing we have learned. Okay? They are applying gradient descent and making the ground truth and train the entire network work for the object detection. Okay? And when training the network, they are having this type of output, but they are applying non-maximal suppression to filter out unnecessary output. And that non-maximal suppression is not done by deep learning. So it is only achieved by this type of, I would say, post-processing. I mean, what they do is they are in NMS, non-maximal suppression, they are list of bounding boxes coming from the network. And also they are having confidence values here, okay? And they are somehow sorting the confidence values, okay? So in confidence value, I mean, they are sorting the bounding box information, which has the highest confidence value. So what they do is they are calculating this, this variable, which means the similarity between bounding boxes. So we are actually using intersection over union when calculating the similarity between bounding boxes. If there are two bounding boxes, we use this intersection over union measure to calculate their similarity. What they do is they calculate intersection region of these two bounding box and divide it by union regions. That's why they are called as intersection over union. Okay, so this is the intersected region, and this is the union region of the two bounding boxes. Okay, I mean, if they are completely same, if two bounding boxes are completely same, this IOU becomes one because union of these two bounding boxes are same as their intersection area. So IOU becomes one when two bounding boxes are same. And if they are completely different, this IOU becomes zero. Are you guys agree with this? So intersected region becomes zero, so IOU becomes zero. Okay, but in the middle, IOU becomes higher if they have higher intersected region, but IOU becomes reduced when they are having less amount of intersected regions. Okay, so this IOU is a measure for calculating the similarity between two bounding boxes. Okay, so here they are calculating the intersection over union measures for all the boxes contained in here. So they are first getting, target for, the boxes with highest score. They are one time selecting it. So they first select the boxes which have the highest score, and they for the remaining boxes, they are calculating the IOU to these things, okay? And then if their threshold, their similarity is higher, then they are removing those boxes because this is highest one. This is the highest one. So if remaining list, in the remaining list, uh, if there is bounding boxes which is having high similarity to this box, then they have to be removed. Okay, and after doing that, they are going to next item and do the same and gradually removing the older list. Okay, and that's actually implemented here. So if you follow this pseudo code, then you can feel that that is actually done here, NMS. Okay. this is, I mean, how to say? This is just a coding implementation, not how to say, not deep learning algorithm, but using this type of sorting and removing scheme, you can manage and apply this NMS. Okay, so they want to reduce unnecessary output here. Okay, they want to remain only the maximal responses having the maximal confidence score. Okay, so this is YOLO. Okay, applying simultaneously they estimate two bounding boxes and class probability for each grid, and then apply NMS. This is YOLO. And this is somehow summary for what we have learned for the object detection algorithm. FPS, that is denoting frame per second. So this is a frequently used measure for calculating some algorithms speed. So 1 second, how many frames are processed? Okay. So if 1 second, within 1 second, some algorithm can process more than 50 frames, then it means it is very fast. Okay. And if some algorithm can process 30 images per second, it is slower than the algorithm that can process 50 per second. Okay. So this is measuring the speed, and if it goes to this direction, it means faster speed. Okay. And here, y-axis, that is denoting the precision, which is the accuracy of the algorithm. Okay. YOLO is here. Okay. It's faster, it is efficient, and but their performance only lies here. Okay, so it is fast, but they could be their performance could be limited. So you can see RCNN algorithm, their performance is here, slightly over the YOLO, but you can see their speed is very slow. Okay, compared to YOLO, RCNN is very slow. But you can see fast RCNN, they are slightly in the right side in the x-axis, but their performance is greatly improved. Okay, so and also faster RCNN is here, so the accuracy is also greatly improved, and at the same time, their speed is also right side of the fast RCNN. But this FPS 30 is the criteria for deciding whether some algorithm is real time or not. Okay. If some algorithm is having FPS over 30, we call that algorithm as real time algorithm. So YOLO, in that sense, is the real time algorithm. But this RCNN, because they are two-stage algorithm, so even though they have more accuracy than YOLO, but they are not real-time algorithm. But you have to also see this YOLO version 2, they are exceeding YOLO and even exceeding the performance of the fast RCNN. Okay, in the y-axis, there's some YOLO version 2, they are many variant. Depending on their backbone architecture, they are having some trade-off even with the same algorithm. Depending on the layers of the CNN, they are having multiple algorithms in YOLO version 2. But some variant of YOLO version 2, they are exceeding the performance of the fast RCNN. Okay. And also they are retaining the real-time efficiency. Okay. So nowadays, many people are using YOLO version, recent version of the YOLO for achieving the object detection. Okay. So this is the comparison, also the comparison in YOLO paper. So they are having different error statistics, but YOLO, they are especially weak in localizing the object. Okay, so I will later explain more about these things. YOLO, they are estimating only 98 bounding boxes. Okay, so I already told that. So original YOLO, they are estimating only 98 boxes from overall image. So if you are having images that have more than these bounding boxes, then they cannot work properly for those images. Okay? If there are many objects inside, then YOLO may fail. Okay? So that's the limitation of YOLO. And subsequent versions of the YOLO, they are trying to solve this problem. Okay? But also, they have low recall, but in precision, actually precision recall, that's two very important measure for measuring the accuracy of the algorithm. But YOLO, they are having good precision, but they are less good having good recall. So recall and precision, I will explain here. So yeah, anyways, they are having low recall. So I mean, that's also because of this limitation, because they have less number of bounding boxes. Uh, even though they cannot estimate some object, even though they cannot capture some object inside an image, that things are not reflected in the precision. That's because why YOLO looks good in measurement, but YOLO is practically not that good compared to RCNN as well. So that's because of the recall, and I will explain that briefly here and then finish today's lecture. So slide is showing the difference between recall and precision. I mean, if some people say a lot, so this is the situation like that. If some people say a lot, uh, then she may have high probability to have high recall but have less precision, which means if she say like this amount of words every day, then she may reflect all maybe many issues happened in that day. Okay, among words she told, this may cover some issues of that day. Okay, but some may be true and some are not true maybe. So how to say, cover all issues of that day, but many will be false. Okay, if some speaks a lot, then that words can cover many issues of that day, many news, many issues of that day, but may be full. I mean, most of things, I mean, half of them could be wrong, okay? But if someone tell just one, let's say he tell 10 word a day, per day, uh, his word uh, cannot cover all news of that day, okay? Because he tells less, so what he tells cannot cover all the things happened on that day. But among 10 words, maybe let's assume he tells always the truth. Okay, so uh, his, how to say, accuracy could be high. Are you guys capturing this situation? So this is similar to what algorithm we developed. I mean, let's say this is some algorithm that produces a lot of responses. Okay. So if some algorithm produces a lot of responses, a lot of bounding boxes, then it can it can capture all the objects inside an image. There would be high probability to capture all the objects inside an image. So that means uh, if some algorithm produces many responses, there would be high probability to cover all the objects inside an image, but many of them will be false. Okay, so this is more about accuracy. Their precision, this is more about precision. Precision that is calculated like all the predictions divided by, sorry, correct predictions are divided by correct number of correct predictions are divided by number of predictions. Okay, but for the recall, what they calculate for recall is number of ground truth object divided by prediction, correct prediction. So I mean, if we have many predictions, then it can cover, maybe it would be high probability to cover all the ground truths. That's actually the recall, okay? But this is the precision. Precision, number of predicts, correct? Oh, sorry, anyways. But I mean, if some algorithms prediction is having less, then I mean, number of ground truths over number of correct prediction. So because their prediction is having less number, so they have less probability to cover all the ground truths. Okay. I mean, this person is similar to YOLO. So YOLO predict less, so they could have high precision, but they have less probability to cover all the ground truths inside an image. Okay, so YOLO has less recall but high precision, but RCNN, their version is having a good balance between recall and precision. So maybe next lectures, we will see how recent version of YOLO is improved and how they can solve this recall problem. Okay. Okay. So let's finish here and see you this Wednesday. Thank you.